A transistor today is 15 silicon atoms wide. That is the entire channel an electron has to cross, and it is roughly the width limit before physics stops behaving. IBM just announced a chip that gets around that limit, not by shrinking the transistor further, but by refusing to shrink it at all. Instead, they stacked one on top of another, and the way they pulled that off explains why almost nobody thought this was possible for another decade. Recently, IBM unveiled what it is calling the world's first sub-1 nanometer chip technology, branded internally as NanoStack. The number attached to it is 0.7 nanometers, or 7 angstroms, and the chip packs close to 100 billion transistors onto a piece of silicon roughly the size of a fingernail. That is about double the density of IBM's own 2-nanometer chip from 2021, achieved in 4 years. Before going further, let me clarify. 0.7 nanometers does not describe an actual physical measurement on the chip. Node names stopped tracking real dimensions years ago. They now function as generation labels, closer to a model number than a ruler reading. Nobody at IBM is claiming a feature was carved 0.7 nanometers wide. So the real story is what forced them to invent a new architecture in the first place, not the label. For 6 decades, chip making followed one instruction, that is making the transistor smaller. Smaller transistors switch faster, draw less power, and let engineers cram more of them onto the same piece of silicon. That single idea is most of what Moore's Law actually was, and it is why a phone today outperforms a 1990s supercomputer. That instruction stops working once the transistor channel drops to around 15 atoms across. At that scale, there is no more room to shrink. Electrons begin leaking through paths they should not take. Heat becomes difficult to manage. The industry has watched this wall approaching for years, and the open question has been, what happens once shrinking is no longer an option? So the new one is IBM's answer to stop going smaller and start going vertical. Every logic circuit needs 2 types of transistors working together, N-type and P-type. Chips have always placed these side by side on a flat surface. NanoStack places one directly on top of the other in 2 separate physical layers. Because the 2 transistors now sit in different layers instead of sharing one plane, engineers can build each one from different materials and tune each independently, one optimized for raw speed, the other for power efficiency. That kind of independent tuning is not possible when both transistors are forced onto a single flat surface, competing for the same space and the same materials. Stacking transistors sounds straightforward until you look at how a transistor actually gets built. Fabrication involves hundreds of steps, many of them at extremely high temperatures. If a second transistor is built directly on top of a completed one, that heat destroys the transistor underneath. This single problem is why stacked transistors stayed a theoretical idea for years. IBM's workaround was to stop building both transistors on one wafer. Each transistor is completed separately, on its own wafer, then the 2 finished wafers are bonded together afterward. The bonding process itself is where this gets genuinely strange. 2 surfaces, polished to an atomic level of smoothness, are brought into contact and begin sticking to each other on their own, held by van der Waals forces, the same faint attraction that lets a gecko grip glass. Heat is then applied, and that loose attraction converts into permanent chemical bonds. The 2 separate wafers become one solid structure. An ultra-thin dielectric layer, kept under 30 nanometers, sits between the 2 transistor layers, close enough to keep performance intact without interfering electrically. The tolerances involved are unforgiving. A single stray particle of dust between the wafers is enough to fail the bond entirely. The 2 wafers must also align with nanometer-level precision, since the top transistor has to match up exactly with the one beneath it, and there is no second attempt once the bond forms. Measured against IBM's 2-nanometer chip, NanoStack is rated for up to 50% more performance or up to 70% better energy efficiency, depending on which the design prioritizes. Either figure alone would represent a full generational jump. The number that drew even more attention inside the industry is SRAM scaling. SRAM is the fast-on-chip memory sitting next to the logic, and it has essentially stopped shrinking for over a decade, becoming the industry's most persistent bottleneck. IBM reports a 40% SRAM scaling gain with NanoStack, the first meaningful improvement in that area in more than 10 years. This is not primarily about a laptop booting faster. Running a large AI model spends a significant share of its energy not on computation itself, but on moving data back and forth between logic and memory. That repeated movement, happening billions of times per second, is where much of the power gets consumed. Stacking shortens that trip. When memory sits physically closer to the logic that needs it, less energy is spent moving data, and more is spent doing actual work. With AI data centers consuming electricity at a scale that is becoming a real constraint, that efficiency gain is significant, and it is likely the main reason IBM frames this announcement around AI rather than general computing. Worth noting, this is not the first time engineers have stacked components. It has already been used in camera sensors, high-bandwidth memory, and flash storage. What is new is applying that stacking approach inside the transistor itself, which nobody had achieved before. This remains a research demonstration, not a production chip. IBM has built and validated a functional inverter and proven the bonding process works. Turning a working lab demonstration into a manufacturing process that produces millions of reliable chips is a separate and much harder problem, and many promising chip technologies have failed to make that transition. Much of the outcome depends on equipment makers rather than IBM alone. Wafer bonding at this precision requires highly specialized tools, and companies like EV Group and Tokyo Electron will play a central role in whether NanoStack ever reaches volume production. IBM conducted this work at its Albany, New York research facility, with partners including Tokyo Electron, Lam Research, and Screen, and is incorporating one of ASML's high-end AEUV systems for the fine patterning this design requires. IBM's own estimate puts a path to production at around 5 years out, a timeline that is both close and far in an industry where plans regularly shift. For years, the assumption has been that Moore's law is running out of room and computing progress is set to slow down. NanoStack reframes that question. None of this is guaranteed. Manufacturing at this precision could prove too difficult to scale, and IBM is not working alone here. TSMC, Samsung, Intel, and IMEC are all pursuing stacked transistor designs of their own. But being the first to demonstrate a working sub-1 nanometer chip is a real milestone, and the ideas behind it are likely to show up in the devices people are using a decade from now.